Hello there, UILCS coders, and in this video, I will cover the heap in Java. So, what is a heap? A heap is a complete binary tree. And what does complete mean? I have an example. So this is an example of a complete binary tree versus a full binary tree. And also, binary trees are just trees that can have at maximum 2 children, which is why we call them binary. So, in a complete tree, or in a full tree, you can see that every single node has 2 children, as you can see here. But on the complete tree, only this node has a child. The ways complete trees work is on this last level, right? You fill the tree like this. So this node, and this node, then this node, then this node. Excuse me. So as long as that idea is maintained, that this is the order you fill in, then you have a complete tree. So if I had this, it's a complete tree. If I had this, it's a complete tree. If I had this, it's a complete tree and a full tree. Right? Every full tree is a complete tree, but not every complete tree is a full tree. Right? This is a complete, but it's not a full tree. Now, is this a complete tree? No, because for a complete tree, the next node should be here. Is this a complete tree? Yes, because it's following that order of filling the bottom row this way. Okay, what about this? Is this a complete tree? No, because the next node should be here, not there. So that's what a complete binary tree is. Now there's the concept of the max heap and the min heap, right? So a max heap is just a complete binary tree where the root is your maximum value, and that's the only thing you can tell. So root is your maximum in a max heap, and then your root is the minimum in a min heap. The idea with a max heap is that the children of a node is smaller than the parent. And in a min heap, so let's say children less than parent to show that they're less smaller than the parent in the min heap. But then in the max heap, children are greater than the parent. Sorry, in the min heap, children are greater than the parent. Now there's no ordering of your children. In the binary search tree, the lower child went on the left, bigger child went on the right. There was no order. You can see I put 4 here, 3 here. I could have very well put 3 here, 4 here. I could put 5 here, 3 here, or 4 here, 2 here. It has to maintain this. And the elements are inserted following inserted in a way that the tree is still complete. So let's cover insertion. So I have the following binary tree, or following heap. I guess it means the same thing. I have a child here, child here, a child here, and then a child here. So you're 15, we'll make it a max heap. So you're going to be 10, you're going to be 9, you're going to be 7, you're going to be 2. Right? Don't think that 9 should be here, 10 should be here. There is no such ordering of children. Right? So let's say I was going to insert the element. Let's insert like 4. Now where does 4 get inserted on this? Because there's no root comparisons. You don't compare with the root. You don't do that in a heap. It gets inserted based on where you are in a complete binary tree, right? Looking at filling out this. We filled out here, we filled out here. So then the next node should be here. So we're going to add in a root. We're going to add in 4 here. This is where 4 is. And is 4 less than 9? Yes it is, so we're good. It's less than its parent, that's all we care about. Everything is good, life is good. Now let's insert 13. So where will 13 go? What's the next available spot? It's here. So I'll simply draw an arrow down here, do a little line, write my 13, but wait, this is a max heap. The parents must be bigger than the children. Is that the case here? No, 9 is smaller than 13. So what are we going to do? We're going to swap 9 and 13. So 9 will be the child now, and 13 will move up to be the parent. We're going to swap them, okay? That's literally as complex as it goes. Okay, I'll do one more insertion, and that is going to be 20. So first off, where will 20 get inserted? Well, if we're trying to insert this, right, we have to follow complete binary tree order. The next element should appear here, right? Because we fill in left to right. So let's add in that element, which is 20 here. Next, we'll do our checks. So you only have to check your ancestral line. Is 20 bigger than 2? Yes, it is. So let's make that a 0, make this a 2. Is 20 bigger than 10? Yes, it is. So let's swap those positions around. I'll erase this. I'm going to erase you now. And so this will be 20, and then this will be 10. Is 20 bigger than 15? Yes, it is. I can have it. Yes. Okay, cool. Big eraser. So I'll erase you, and I'll erase you. And now 20 becomes our new root. And that's generally it for insertion. So insertion has a best time complexity of O of 1. And this is when you have to make 0 swaps, right? When you can just insert the element at its proper place. And then it has a worst sizing slash average time complexity of O log n, because you're just traveling up the tree, and trees are, an insertion in a tree is typically log n. Or well, it's just the idea that when you're in a tree, everything splits off by 2 here, so it's be log 2n, if you want to get specific about it. Swaps. On average it's this, and then also worst is that too. This is just a tree. Wait, O log n. So worst, let's see, sorry, best, it's the smallest time complexity. This is average slash worst case. Now, there's one idea I want to talk about that I didn't talk about yet, which is the array representation of a binary tree. And more specifically, it's going to be a representation of a complete binary tree. So particularly complete. Okay, so what do I mean by this? So in an array, so I'll have an array here, here. Let's take this tree, and how would I insert it into the array? Well, you go level order. So I'm going to have 20, comma 15, comma 13, comma 10, comma 7, comma 4, comma 9, and then lastly, comma 2. So we're starting at index 0, 1, 2, 3, 4, 5, 6, and 7. So everything said, how is this a tree? Where's your parent? Where's your children? Well, you can find your, let's do it like this. Let's start with left child. So your left child is equal to, and you have to know these formulas, 2 times your index plus 1. Okay, that's your left child. Now your right child is going to be 2 times your index plus 2. So 2 times I plus 2. So we have the left and right child. Then your parent is the floor of, I think it's, okay, it's floor of I divided by 2. Sorry, not I divided by 2. I minus 1 divided by 2. And I mean, this makes sense, right? Because if you're looking at our left child, let's say the formula is 2I plus 1, right? And this is your index of your parent, you're saying. And this is your, let's say, left child. Right? And then n is the index of your child. Then if you're trying to go from parent to get the parent index from this child index, it'd be n minus 1 over 2, which is I. And what's that? That's the formula. So this will get you the parent index, and what does this do? Is get you the parent index. Why is it floored? Because binary trees will have 2 children and they have the same parent. So we need to make sure the right child is attached to the left child's parent. Okay, so let's go to this example again using only focusing, and I'll take this, it's important, but I need room, so let's move it here. Focusing on the array representation. So we are inserting 4, so this is going to be our array. 20, 15, 13, 10. I guess it didn't always look like this. Well, then how about this? Let's use this array and let's insert some elements. We're not going to insert it to the tree, we're going to insert it to the array. So the next element I want to insert is 50. So 50 is going to be here. Now we said we need to see if the parent is less and swap with the parent. So first let me write the indexes up here. So it's a little bit easier to work with. So 8 divided by 2 is 4. Even if you float that, you're going to get 4. Or sorry, I minus 1 divided by 2. 8 minus 1 is 7. 7 divided by 2 is 3. So the parent of 50 should be 10. And does that correlate with the tree? Yes, because where would this node spawn if we're doing a complete binary tree? It would spawn right here. So it would be the child of 10. I'm not trying to save right now. Okay. So 8, 10, right? Is 10 less than 50? Yes, it is. So we need to swap. Boop. 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 Alright, let's check again. The parent of index 3, so be 3 minus 1 is 2. 2 over 2 is 1. Does that make sense? Yes, because here we're at 10, the parent was 15, and I'm not going to keep updating the tree. You can do that by yourself if you'd like. But yeah, so I'm just confirming that the parents are right. Right, so this is the parent of index 3, which used to be 30. And is 15 greater than 50? No, it's not. So let's swap it again. Okay, let's try one more time. We're gonna do I, so just I minus 1 over 2 to get the parent. 1 minus 1 over 2 is 0 over 2, which is a 0. So this is the parent. Does that make sense? Yes, 20 is the parent of what was 15. So is 20 bigger than 15? No, it's not, so we need to swap it again. And this is how you do insertion. Now the reason I'm showing you this is because we code a heap without pointers. So you're not going to get this tree representation. We code a heap using an array. Because we can take advantage of the fact that a heap has to be a complete binary tree, and we can represent a complete binary tree very easily inside of an array just by going at the level order of the array. And average works to log n because we're still just following tree methods. We're still operating this as if it's a tree, so we get that O log n benefits. Let's insert one more element. It's going to be, let's do like 17. I'm interested in seeing where that ends up. So 17 should be the left child is 7. I haven't done a good job in updating my tree representation, so it's not gonna look like it's not gonna be up to date. But hopefully, if y'all are making this tree, then it should be left child is 7, is index 9. So then note when you're making your array, it might be nice to have a size indicator and then also a resize function. Don't use array.length because when you resize an array, you typically double its length by 2. So if we're trying to insert the end of the array every time, we're going to have a huge gap of elements. We don't want that. Okay, 9 minus 1 is 8. 8 divided by 2 is 7. Right parent. Well, 17 is bigger than 7, so let's swap them around. So 17 will go here, while 7 will go here. 4 minus 1 is 3. 3 divided by 2 is 1. 20 is bigger than 17. So no, we're not going to swap anymore. It's going to stop like here would be so 17 is. Or no, 17 would be here. It would replace 7. Now let me swap. And now 17 is properly added into our array. One thing I want to talk about is this. So can you represent an array representation for an incomplete binary tree like this one? Yes, this is possible. So let's say this is A, let's say this is B, C, D, E, F, G. So this is not a complete binary tree because there should be a child and a child here. There's not. But how would this look like? In array representation, it'd be A, comma B. Then you have like some filler, like empty space. Maybe you could have some sentinel value or just null or whatever you want. Empty space, E, F, G. So this will still maintain the relationship of the tree because we're just saying, hey, these two elements are supposed to be children of. Oh, this is a little bit wrong. Sorry. It should be A, B. We're going in level order. So E, then your two empty spaces, then F, then G. That's taking it level order. Right. And this is saying that, oh yeah, these guys are all children of B. Yeah, you can use the formulas if you want. It'll show you that. Okay. Let's go over deletion. And the principles I'm doing here, I'm using a max heap. I'm going to use a max heap for deletion 2. To do with a min heap, instead of checking if an element is greater, you check if an element is. You don't swap an element is less, you swap an element is greater. Because in max heaps, the biggest elements are at the bottom, are your children. Or are your leaf nodes. Okay, deletion. So let us take this binary tree that I've already made. So I'm lazy. Let's just copy it over. Copy, paste. Here delete you. fill in this top bit there, right? This is a binary tree, and I want to delete E7 node. Well, actually, this is never gonna happen in a heap. In heaps, there's one element that we really care about the most, and that is the root element. It is the only one we know that's a maximum or a minimum. It's kind of like our favorite element. In heaps, you only delete the root, so we can only delete 20. Excuse me. I'm going to delete 20. 20 is gone. Before I delete 20, well, which element comes to take its place? Right? Well, if the root still needs to be greater than the parents, right? So if 20 is gone, then, or the root still needs to be greater than its children. So if 20 is gone, be greater out of 15 or 13 should take its place. Well, 15 is greater than 20, so we'll move it up. So 15 will go here. But now we have an issue here. There's no element here. What should take its place? 10 or 7? Well, which one's greater? 10 is greater. 10 will take its place. 10. Well, now we have an issue here. Nothing here, which is greater? 2 or nothing? Well, 2 is bigger than nothing, so 2 will take its place. And now here, nothing or nothing? Well, that's nothing will take its place. And then what is nothing? It's nothing, so this will go away. Right? You typically end up deleting what in a tree we've learned already that the only node that actually gets deleted is always the leaf node. Only leaf nodes get deleted from the tree. Okay, so let's focus on deletion from this binary or this heap. So when you delete from a heap, you only delete the root element. Okay? So I can only delete 20. You can't delete subchildren from a heap. This is true for both max and min heaps, and the idea is that 20 is like the prize of the heap. In a max heap, it's the maximum, and the min heap, it's the minimum, so it's what you'd want. So we want 20, so we're going to delete it. Now what comes to take its place? The last element, which would be 2. So we'll not swap, but replace 2 with 20. It'll just be easier for us to do this. Oh, well, let's let me move it now. But what does that mean? It means we're gonna have to do some swaps. And we'll also set this index to null, so it'll go away. We're making it empty. Now we just have to do the standard swaps, right? Because the large element should be at the top. Well, how are we going to decide how we're going to do our swaps? We're going to compare the children, so 15 and 13. And whichever one's bigger, we'll swap up. So 15 is the biggest child. And then, sorry, we check if 15 is bigger than 2, which it is. So then we swap 15 with 2. Then we see, do we need to do any swaps? 10, 7, 10 is the biggest, but is 10 bigger than 7? Yes, it is. So 10 will go up here. Sorry, but is 10 bigger than 2? Yes, it is. The answer is yes. 10 and 2. Okay, yeah, and that's essentially just it for deletion. I looked in my notes, I had a lot written on deletion for some reason. It's not that much to it. Let us delete the next root now. Just remember you're deleting roots in a heap because the root is like the prize. So we'll delete 15. The smallest child, or the not smallest, but the last element in the array should be the furthest out level order wise, which is 9, or the last child in the final row. Either way, however you want to look at it. It'll be 9 in this case. The reason it was 2 before is because we had a little guy here, which made it still last, but now that he was killed, 9 is the last. It's not that we go from left, we just go from the last place. So 9, we've done our swap. Let us set this value to null. Okay. Now we'll complete our swaps. Okay, let's do our swaps now, sorry. 9. Compare that with 10 and 13. 13 is bigger. Is 13 bigger than 9? Yes, it is. So we shall swap this. Our new root will be 13, and our right child will be 9. So we're going to declare 4 and nothing. 4 is bigger than nothing, but is 4 bigger than 9? No, it's not. So that's where 9 will rest now. I could go over it one more time, but I think you get the general idea. In insertion, if I were to write out steps, step 1, insert at index size. Right, size is 0, size is 1, size is 2, size is 3, size is 4, size is 5, size is 6, size is 7, size is 8. Once we add in the 8 element, we'll increase size to 9. And then what do you want to do? Swap if needed. Just 2 steps. Best time complexity, O of 1. Worst average, O log n. Deletion. Step 1. So, replace parent with index size, or I should say with alum at ISI, so at the last one that we have. And then step 2, we are going to swap. Swap if needed. Well, actually, I want to make that step 3. Step 2 will be delete empty leaf. Because as we replace the parent with the last element, we will now have an empty leaf. We want that to be removed. So what does that mean? Not deleting an element from the array. Going to set size and decrement it. So now size will be 1 less. Size represents the last array. Right? So now the last array element will be, if it was this guy, now it'll point to this guy. Size will point to 4. And now lastly, we will swap if needed. Excuse me. So I want to do one more deletion practice, but let's do it with the array of this tree. That's going to be 13, 10, 9, 2, 7, 4. And also it makes sense why we'd want to start here, because it's just an array. So if you try to delete any of the position, you'd have to refactor everything, move it around. Then what's even the point of using a heap? Just use an array at that point. Okay, so let's go over this. So I'm going to delete the root. So 10 is going to be replaced with the value of size. Size is pointing to this 4. So we're going to replace u at 4. And also, I know I'm drawing the array like this. Really, the array is long, right? It has a bunch of empty values here. The array has a bunch of empty, whatever you say, like probably 0 because it's integer, Here's the default array values, right? Size, so that's why we use size. We use the size as a pointer, sort of, to point to the actual true end. This is the end of our heap before. And so we're gonna say this end is here, but let's do something. So instead of deleting 13, just removing it forever from my array, let's make the last element 13. Okay. Now we can do our swaps. So compare the children of 4. How do we find the children again? Well, first let me write out my positions. And then that's, or 4 will be here. So the child, left child, we said, was 2i plus 1. And then we said that right child was 2i plus 2. So then 2i, if this is 2 is 0, plus 1 is 1, 2 is 0, plus 2 is 2, so 10 and 9, yes, that makes sense. We're going to see, is this one bigger than this one? Or which one's bigger? Well, 10 is bigger, but is 10 bigger than our current root of 4? Yes, it is. Let's swap. So now we have 4 at 1. So we're going to see is 4 greater than this children. 1 times 2 is 2, plus 1 is 3. 1 times 2 is 2, plus 2 is 4. So we're comparing against 2 and 7. Well, 7 is bigger, and between 2 and 7 is 7 bigger than 4? Yes, it is. So swap everything around. And then here we have 4, and where's 4? It's at the end now. What could it compare to? Well, there's nothing for it to compare to. 2, 4, okay, let's do 4 times 2 is 8. 5, 6, 7, 8, 9. 4 times 2 is 8, 8 plus 1 is 9, that's 0. 2 times 4 is 8, 8 plus 2 is 10, that's 0, 0, 0 is 0. Is 4 bigger than 0? Yes, it is. So we're just going to leave it there, and that is that. To kind of see a base case emerge, the base case is essentially just when we don't have to move the element anymore. Or you could say it's when its child and parent are smaller than the current root. So we can make this recursively. In fact, I'm going to program it recursively. I don't know. Check with UIL because UIL added a heap one year. I'll see if they made it recursively before I actually start the code for this. If they made it recursively, we'll do it recursively. If they made it iteratively, we'll do it iteratively as well. That's no problem. Okay. Now I want to delete 10. Let's delete 10. The last element is 4. 4 will come to take its place. It's kind of crazy. 4 was literally like just the root. Now it's back up, but that makes sense, right? So our size, of course, now we swapped, we need to decrement size by 1. And I'm also just gonna highlight this in red. Let's move on, let's for swaps. 7 and 9, 9 is bigger, swap it around. Okay, 2 and nothing, right? 2. And technically, 3 times 2 is 4, plus 2 is 6. I'm thinking doing this one out further. Your size is your limiter. Now I want to delete 9. So size is pointed at 2. So we'll swap them around, just like this, just like this. Okay, let's compare to the children 7 and 4. 7 is bigger than 4, and it's bigger than 2. So we'll swap them around. Alright, is 2 bigger than children 4 and nothing? Well, 4 is bigger than nothing and bigger than 2, so we're going to swap them around. So you see there, you can't say I mistakenly said right child is greater in size or something, then we can do it. Then we can return, have a base case. But that's not true because your left child could still be bigger than your current root. And we need to account for that for heap. Or particularly I'm doing a max heap. Okay, but now everything's in place. Let's delete 7. So to the size should have decremented over here now. Well, 7 and 2 are going to swap. So the size wouldn't be here. I forgot to decrement size for the last one. 2. Size will be here. Okay, let's compare to let's compare children. 4 to nothing. 4 is bigger than nothing, so we'll see is 2 bigger than 4. Is yes it is. Or is 2 smaller than 4? Yes it is. So we'll swap it around. Okay, let's take this size. Let's decrement it by 1 again. So at the end, right? Oh no, size is still here. Sorry. We've sorted it now. Let's say I want to delete 4 now. So I delete 4. I replace it with 2. And then I increment size by 1. Or decrement it by 1. So size is here. Well, the left child of this is now past size. So we can just stop, return, and then that should just be it. Right? We should keep on calling this all we wanted. Keep on trying to remove this, remove the root. There's nothing to swap with. I guess if you removed it, I don't know what happened. I'm gonna have to Google that. I mean, I just imagine if you try to remove any further, it would just do 0 or 0. But you'd be stuck infinitely. As I won't think about it. But yeah, look what we've done here, okay? If I just remove the size pointer for a second, allow you to look at the full array now of whatever previously are elements. Of course, ignoring all this empty space which we didn't use, so you might, right? Maybe we store the old or initial size somewhere, which would always point here. So we cut off here, right? What have we done? We've sorted the elements from lowest to highest. So this is the process of the heap sort. What is the heap sort? First, insertion of everything. You insert all elements. So it'll take a random array, insert all the array elements to heap. And then it will remove all elements. From heap. And then it will simply return the array. Now probably it'll be code to take this array, this section, put it in a new array or something. Or I don't think you need to do that, because in heap sort, you're never going to go past the size. So you probably just store a reference. Maybe you not even have to do that. You probably wouldn't even worry about that. You just move size along. I'm worrying about it because I have to code it like soon. Right around at the time. But if we have a max heap, that's gonna what the biggest values, which is our root, are gonna end up at the end, right? So you could say it's gonna sort from lowest to highest. If I have a min heap, well the biggest values are gonna be at the front, the lowest values are gonna be at the end. Or the lowest value is gonna be the root, so it's gonna go from high to low. That's the difference between a min heap sort and a max heap sort. For time complexity, it's just pretty much O of n log n for like everything. Because it's just gonna go through, you're gonna go like up the tree, right, following the parent thing, so log n. But you're gonna do it n times. So the next thing we need to talk about is heapify, and what that means. So I have this array, 5, 10, 12, 3, 9, 4, 6. Because this is level order, we can say that currently the tree looks like this. 5 here, 10, 12, and then 3 will be here, 9 will be here, 4 will be here, 6 will be here, 3, 9, 4, and 6. So let us conduct heapify on this array. It's just some array. And heapify is really just turning an array into a heap. So like I said, we had steps for heap sort, we had steps for remove, we had steps for insert. The first step is start at I equals size. And then we're gonna like step 2, swap if needed. Lastly, step 3, I minus minus. So let's start here at size, which is 6. Okay, let's swap. How do we know the swap? Let's compare with its parent. So this is 0, 1, 2, 3, 4, 5, 6. 6 divided by 2. 6 minus 1 is 5. 5 divided by 2 is 2. So this child is, the parent is 12. Is 12 greater than 6? Yes, it is. Okay, so what are we going to do? Nothing. There's no need for a swap. Decrement s. S is now 4. 5 minus 2 is 3. 3 divided by 2. 5 minus 1 is 4. 4 divided by 2 is 2. Compare the parent with 12 with 4. 12 is bigger than 4. There's no need to do anything. Decrement I. 4 minus 1 is 3. 3 divided by 2 is 1. Compare 10. Compare 9. 10 is bigger than 9. Don't do anything. Decrement s by 1. Okay, 3 minus 1 is 2. 2 divided by 2 is 1. 1 is 10. This is 3. Obviously, 10 is bigger than 3. Decrement I by 1. Okay, 2 minus 1 is 1. 1 divided by 2 is 0. 0 is 5. That's the parent. 5 is less than 12. We need to perform a swap. So we've swapped now because we need to 2, so 12 is here, 5 is here. I don't know why I'm reading red, I guess. It's just a good swaps happening. Decrement I, that's it. That's no more swaps are needed to occur. Let's just don't have any parents? No. It'll point to itself. Decrement s by 1. 10. Its parent 1 minus 1 is 0. 0 divided by 2 is 0. Is here. Is 12 bigger than 10? Yes, it is. No need to do anything. Decrement s by 1. It's at 12. 12's parent is 12. Is 12 bigger than 10? No, but it's equal to 10. It's equal to. Is 12 bigger than 12? No, but is it equal to 12? Yes, this is where we stop. So let's update this heap with the reflected changes. So all we did was really just swap this 5 with 12. And we're making a max heap here. See, did I make a max heap? 12 up here, and then 5 here. Oh no, because I forgot to check. I'm sorry. I forgot to check something when we're over here. When we swapped 12 and 5, sorry, you don't check this anymore because everything else in the heap should be good. You need to check this with its children is left and right. Sorry, that's my mistake. So let's check 2 times 2 plus 1 is 5 is 4. 2 times 2 plus 2 is 6. 6 is bigger than 5. We'll swap them around. So, lastly, can 5 go anywhere? No, it has no children. That's it for 5. So this should be 5 here, and this should be 6. And what is the structure we've made? It's a heap. Right, lower, all these are lower than you, all these are lower than you, and then all of these are lower than you. Heapify has a time complexity of O of n. And this is its worst, best, and average time complexity. Because you're moving this pointer what n times? So at best it's O of n, at worst it's some multiple of O of n. Not O of n squared or anything, just like O of n times some value. But that can simplify down to O of n. The last topic we need to discuss is the priority queue. The priority queue is a queue that sorts elements, and it's actually backed by a min heap. So if you're sorting in natural order, say min heap, reversed, if you pass in comparator dot reversed, excuse me, it is going to be a max heap. And then you can make your own custom comparisons. That's just a heap. You can't, it doesn't really, it's kind of wavy waters whether it's a min or max. But you really need to know this one. Because a priority queue that you'll be tested on is in natural order. Normal priority queue, nothing passed in default natural order. And a higher priority queue is implemented using a min heap. So what does that mean in terms of time complexity? So your poll is O log n, right? Your removal of deletion of elements is O log of n. We said that earlier. Your offer is O log of n. Your adding of elements can be O log of n. Then your searching contains is simply O of n, which we've discussed before. It's the same as before. Your peak is O of 1, as it should be. And then I guess we have size everywhere on my list. It's also O of 1, but okay, who really cares about size, I guess. But if we compare that to a queues, which queue uses is backed by an array. So I believe a queue is faster. Yes, queue. So the time complexity for all operations on a queue is O of 1. So all of this is O of 1 on a queue, and I explained why in my queue video. Okay, so let's code ourselves a heap. I said we need a tracker for size, and then we're going to need an array of elements. Public void or public state heap. So this will create size as 0, and I will initialize the array as a new integer array. Let's pass in the capacity. It's typically how array backed things work. Yep, just like that. Okay, cool. So I want to add a insert method, int element. So the first thing to do is we're going to insert this at the last element of the array. So r at size is equal to ln size plus plus. So this will handle step 1, add to end. Now we need to check with parents. So what should our while loop be? Well, let's see. Let's first get int parent is equal to your, if you're going off of the current index here, I'll say incur is equal to size before we increment size by 1. The parent is going to be equal to current or mat dot floor current divided by 2. This is not legal syntax. Yeah, because that tends to double. So then actually, we're just doing integer division here. That'll work. Okay, so we need to get the parent. We need to see if the parent array element is bigger or smaller than the array at its current index. And if that's true, we want to swap elements. Let's say int temp is equal to the array at parent. Then array at parent set it equal to your array at cur. Then lastly, array at cur set it equal to temp. Now we need to do one last thing, we just need to swap our pointers around. So parent, so let's say int temp parent. Okay, let us set cur is equal to parent, or temp is equal to cur, or sorry, parent is equal to cur, and then cur is equal to temp parent. So now our pointers have moved up. While true will make it go on forever, but we can't go on forever, right? When parent is equal to 0, we should probably stop. No, because we have an element at 0. So how are we gonna handle this? Okay, so let us code in a remove function for the heap. Let me delete all this. What do we need for the heap? Step 1. Find, raise up into multiple steps. Access the root. I will say r of 0 is the root. First, so we can access the root. Okay, I know how to do that. Let's make step 1, then maybe swap the root and the value at I is equal to size. I know I said size in the videos. I said size because I was starting this at -1, the examples and stuff. I'm starting this at 0 here, so that way this doesn't have the opportunity to be -1. Just makes the code simpler. Because obviously array at -1 is an error, so not an error, an exception. But so first let's do this. So what I need to swap, I need a temp variable. I'll store r0. I will call this old root. This will also be what gets returned from this. So in case you want it, I don't know, right? And then we need to swap with the value I minus 1. Say r at size minus 1 is equal to old. Right here, probably says r at 0 is equal to r at size minus 1. And then r at size minus 1 is equal to old root. So this will swap them. So after we swap them, what do we need to do? We need to decrement size by 1 to shorten off our heap. So now we've shortened. So now we're looking at the right amount of data. Let us code our while loop. So our while loop should realistically only go while the array at some current value. What should current be? Current should start off at the root, right? Because we're going from the root down. So say int cur is equal to 0. So while this array value is less than its left child, and our cur or it should be less than the left child or I have curs. Oh here, let's make it simpler. While our cur is not greater than left child and our cur is not greater than right child. Because if it's greater than both, then we found its place. Let's not do any more swapping. Int left child is equal to cur times 2 plus 1. Int right child is equal to cur times 2 plus 2. Then either run some checks. If left child is greater than size, so then, and here if left child is greater than size, well, what does that entail? Left child is greater than size, then we don't have any swaps going on. Or let's not worry about that right now. And what if we handle those checks in here? Well, no, we have to worry about it, right? Because it's going to be R of left child, R right child. Or you know what we can do for the time being? Let me just make this true and we can come back to this case later. So I can say left child is equal to cur times 2 plus 1. Right child is equal to cur times 2 plus 2. Okay. Step 1, we said when we're swapping, we'll come back to the conditions a little bit later. We said when we're swapping that we'd swap with the greatest child. So I will say int greatest child is equal to, well no, we can't really say that. I was going to do like maybe a math.max, but let's do like this. Our left child is less than r dot right child. Then I can say that r dot left r dot right child is the greatest child. So what if I define an int greatest child is what we compare with? So I'll say maybe set greatest child equal to right child, else make greatest child equal to left child. So now we have greatest child set up, so it'll either be the right child when the right is bigger, the left child when the left is bigger. So let's say if the array at the current value is smaller than the array at the greatest child, we need to perform a swap. So I will say int temp is equal to array at greatest child. Array at greatest child, you can say is equal to array at cur. Array at cur says equal to temp. Now, can we end it here? No, we can't, because our current value, whatever value we had at current, is now moved to be at the index of greatest child. So we need to update current accordingly. Right, this should always be pointing to that node that we're looking at, the one that we're trickling down. Greatest child can stay, that should be fine. Else, let us, so I'll write another else if array current is greater than array at greatest child, we can simply break. Now this is the general algorithm set up. We need some checks though, if because what happens if left child is greater than the size of the array? What happens if right child is greater than the size of the array? What do we do in those situations, right? Current, if we don't have to worry about current being greater, don't have to worry about that. I mean, we can still worry about it. Why not? Let's write some cases. Let's write some edge cases. If current is greater than size, return or break. So let's leave the loop because whoa, there's nothing for us to do here. If we try and plug in current or left child or right child, we are going to run into an array out of bounds exception. And firstly, if array's left child is greater than size, let's break. I'm sorry, these should be greater than or equal to because size is the end all be all. If not, if we do left is greater than size, this would let us have left child equal to size, and that wouldn't work for the array. We get an array index at a bounds exception. So let's do this. Now, can we say if the right child is greater than size break? No, we cannot say this because in the situation where, okay, right child may be out, we still need to check if left child is less than size, and if it's less than size, if it's greater than. So maybe I can just say in here, if left child is greater. Well, it would have already broken here, so we're assuming left child is less than size. Let me compare the array at left child, see if its array is greater than the array at current. If this is true, then let us swap the two. And then I'll break here because we won't be able to do anything else at this point. If we're at this point, that means like maybe like one left child left, like the last one that we could potentially swap with. If we try to go any further, we would hit everybody out of bounds. So this would be the last swap ever. And otherwise, if it's not true, then let us simply break again because there's nowhere else for us to go. Have to correct that for a second. So let's run this. So does the code work? Yes, it does. 20 gets swapped in accordance. Right, 30, we have it moved to the end of the array, so it gets swapped here. Earlier our array is looking like this. So this is a successful removal. We've gone over the time complexities for everything in here. I'll go over them one more time. Insertion has a best case of O of 1, average and worst case of O log n. Deletion, everything is O log of n. I don't think I covered that. It's just, if you don't know, well, just pick O log n. It might be right. It's probably right. Heap store, everything is n log n because you're going through every element. You're going to, it depends on the size of your array. Priority queue, remember, offer and pull are O log n. Think of them as just remove and insert for a heap. Everything else is normal, just no queue time complexity. And lastly, heapify is O of n. Hope you learned something with heaps. I sure did. I've learned that I should not be trusted when it comes to working with the array. Give me pointers. Oh, I can do pointer code. Give me an array and I just break. But yeah, okay, cool. That is the heap data structure in Java.